learn about the channels, the channels characteristics. If we can recall back in chapter 2, we learned about the fiber optics in general, including the type of fiber optics. Yeah, we have learned about the step index type. We have learned about the grid index type. We have understand what is meant by single mode fiber. Yeah, we also learn about the multi-mode fiber, and also the way how the light propagate in the fiber optics, which is based on the Snell's law. Okay, so that are the things that we have learned in chapter 2. And then in chapter 3, we have learned about the transmission characteristics in optical fiber, which we have learned about the attenuation factors. We also learn about the dispersion factors in the optical fiber. So these are the things that we have learned in chapter 3. Yeah, so basically we have covered everything related to the channels, the fiber optics, and I hope that you understand well on the fiber optics itself. Yeah. Okay. So from this lecture onwards, we're going to learn about the source, the transmitters. Okay. So chapter 4 will be dedicated towards the source. Yeah. So we're going to learn 2 types of optical source. The first one will be the LED, light emitting diode, and the second one will be the laser diode. Yeah, so 2 main devices or 2 main sources for optical communication will be discussed in this course. That will be the topics in chapter 4. So and in chapter 5, we're going to learn about the detectors, the detectors, which is the receiver side. Yeah, the receiver side. So that will be learned in chapter 5 lah. Okay, so combination of chapter 2, 3, 4, and 5 will be basically covering all the components in communication system or in the optical communication system. Yeah. Okay, so without further ado, let us proceed with lecture 7. We're going to learn about these topics, the light emitting diode. So you can refer to the course information, on this chapter 4. So as what I mentioned before, so there should be 2 main components or 2 main devices to be learned in chapter 4. First one will be the LED and followed by the laser diode, later on at the part or lecture 8 after this. Okay. So we have learned that the starting point of the optical comm system will be the transmitter. So this is what we have discussed before. So what is the purpose of transmitter or optical transmitter? So the main purpose of the optical transmitter is to convert, the electrical input signal into light for transmission over the optical fiber. Because we know that the signals that we are actually transmitting in optical fiber will be light, right? But before that, the information or the signal is in electrical input based signal. So the purpose of transmitter is basically to convert this electrical input signal into a light which has been modulated, and the modulated light will be then transferred or transmitted using the optical fiber. Okay, so that is the purpose or the functions of optical transmitter. So in terms of modulation of light, there are few methods that can be used. And I believe that you have learned in PCOM in 3rd year on the modulation. Okay, there are a few types of modulations. We have the FM, we have the AM, we have this digital modulation, the ASK, FSK. So all of these are the modulation methods that can be applied in the optical fiber communication system. So, but our interest will not be on that modulation. We know that this kind of modulation can be applied on the optical system, so on the transmitter itself. Okay, and one more thing to remember or to know is that the conversion from the electrical to the optical signal will require a circuit which is called as a driving circuit. The driving circuit. So driving circuit is a special circuit at the transmitter side, which is used to convert the electrical to the optical signal. Right. So in general, the transmitter consists of this component. Okay, we have a light source. Okay, that should be the main components, the light source, right? And then we have a driving circuit and also the voltage supply. Yeah, because a light source will need a voltage supply to function. So basically, this will be the main components in your optical transmitter box. Yeah. Okay, and these devices, these three devices, the laser source, a light source, the driving circuits, and the voltage supply is said to be mounted in a package. Okay, so we're going to have a box. Yeah, and this package will be then located or placed in a very close position with the optical fiber, so that the light can be coupled efficiently to this optical fiber from this transmitter. Okay, right. So this is a coupling, yeah, a coupling of light from a transmitter to the optical fiber, right? So as what I mentioned in the early part of this lecture, there will be two types of light source that will be covered in this chapter 4. The first one will be the LED, yeah, the light emitting diode. And then we have the laser diode. Yeah, so we're going to start the chapter 4 topics on the light emitting diode. Yeah, the LED. Okay, so this laser diode and LED, yeah, laser diode and LED basically are differentiated. I said to be differentiated by the behavior of the light transmitted by these sources. Okay, for the laser diode, we're going to have what we call as a coherent light that will be transmitted by the laser diode. Whereas for the LED, light emitting diode, the light transmitted or light produced by this LED is said to be incoherent. Okay, these figures basically can be used to explain what is meant by coherency of light. Yeah? So the coherent source means the frequency and waveform of light are said to be identical and their phase difference are said to be constant. Okay, so that is what meant by the coherent, yeah, coherent source. Okay, so that is why we can say from this graphical representation of light propagated by the laser diode, when somehow the wave is said to be, the phase difference of the wave is said to be constant, as opposed to what we have in the LED, right? So we can differentiate from this diagram what is the meaning of coherent source. Yeah, coherent source. That is why in a long distance transmission, yeah, long distance transmission, the preference will be on laser diode. Yeah, laser diode to be used as the light source because of the advantages that is actually offered by the laser diode. Yeah, as opposed to the LED, if we base on this diagram and incoherency of the source, the LED can only be used for a short distance application. Okay, so that should be the difference in general between the laser diode and the LED. Yeah. All right. Okay, these are the general requirements of light source in optical system. Okay, number one is that the emitted wavelength from the light source need to be compatible with the loss spectrum of the glass fiber. Okay, so this is what we have learned in chapter 3 before on the absorption, on the dispersion, yeah, on the scattering, in which we have learned that there are three main windows for the optical system, namely at 850 nanometers, then we have at 1310 nanometers and 1550 nanometers. Yeah. So we need to produce a light source, or we need to have a light source which can operate, yeah, which can operate at this particular wavelength, such that we can take advantage of the loss of the low loss spectrum or low loss offered, yeah, by this wavelength. Yeah, preferably we are going to work at 1550 nanometer wavelength due to very low loss, yeah, offered by this particular wavelength. Yeah, so that should be the first criteria. the wavelength produced by the light source must be compatible to work at these three wavelength values. Yeah, that should be the first one. Okay, number two, this light source must be able to modulate the signal for high data rate transmission. Okay, so this is the very important characteristics. Yeah, so modulation of the light, yeah, for high data rate transmission must be fulfilled. Yeah, so that's why for high data rate transmission we prefer to use a lens diode. Yeah, because of this ability. Yeah, to modulate the signals. Okay, that's number two. Number three, we have learned in chapter 3 that spectral width is one of the important characteristics in which it will determine the value of pulse dispersion, yeah, of light, yeah, pulse dispersion of the information, yeah, of the data. So we need to ensure that the spectral width need to be narrow, such that if we have narrower spectral width, the pulse dispersion will be reduced. Okay, so this is what we have learned in chapter 3 before. Yeah, we need to ensure that the spectral width of the light source need to be reduced or need to be narrowed as much as possible. Okay, right. Number 4, the laser source need to have a high radius in which this will be good for effective coupling into a fiber optics with a small numerical aperture. Okay, it means that the light source need to have it is possible for the light source to have high radiance, means that ability to radiate the signal, yeah, high radiation of the signals, so that more light can be coupled into the optical fiber, although it has a very small numerical aperture. Okay, so we have learned in chapter 2 about the numerical aperture, in which numerical aperture is a characteristics of the optical fiber, which indicates the ability of the optical fiber to receive the light, no? To coupling the light, in which it is related to the acceptance angle value. Yeah. Okay, so this is how we have learned in chapter 2. Okay, again, all the things that we have learned so far in chapter 2 and 3 will be used again. Yeah. Okay, that's number 4, the 4th requirements. The 5th requirements basically must be a stable output power. Yeah, stable output power, that should be a requirement. Yeah, so we want the output power to be stable as much as possible, because we don't want any intermittent values of the optical power. Yeah, because we want the transmission to be stable. There should be no interference, yeah, throughout the optical fiber transmission. Okay, and number 6 will be long lifetime. Yeah, long lifetime, reliable. Yeah, and it must be possible to operate at room temperature. Yeah. Okay, and the last one will be low cost. Yeah, for sure, low cost. You want to reduce the cost as much as possible. So these are the general requirements of the light source that will be preferred in the optical communication systems. Yeah. Right. Okay, so before we can start learning about the LED, we need to understand first about the concept of bandgap energy. Yeah, concept of bandgap energy. I'm not sure whether you have learned about this bandgap energy before, but most likely these topics shall be learned in physics, I believe. I believe, but not sure whether you have learned this or not. Yeah. Yeah. Okay. So you know that basically the light source is said to be produced by using a semiconductor material. Okay. So we understand this because as what we have learned in year 2, basically in electronics. I believe that you have learned about the diode, right? The diode, a PN junction diode. Okay. So this PN junction diode that we have learned in electronics, basically the concept of this PN junction diode are the same with the diode that we're going to learn in this chapter. Yeah, the concept is the same. Yeah, the PN junction diode. So this topic is also covering the p-n junction diode. But the difference is that the semiconductor material used in this diode fabrication. So in electronics, the diode that, the metal used for diode fabrication is mostly silicon. Yeah, mostly is silicon. But we know that silicon will not produce light. Yeah, silicon will not produce light. Okay, silicon will only produce heat. So when we have a driving circuit, we have applied voltage to this diode. Okay, light will not be produced by this p-n junction diode, that we use in electronics, but it will only produce heat. But the difference with the p-n junction diode that we're going to learn in this chapter or use in the light source is the semiconductor material used is different. So in LED, or in laser diode, the material used in diode fabrication is normally called as luminescence material. So what is meant by luminescent material? So luminescent material is a material which can produce light or photon, photon or light, when excited by certain value of current. Okay, so hopefully by this you can differentiate what is meant by diode that you have learned in electronics in year 2 and the diode that you're going to learn in optical comm system. Yeah, the difference is on the material used for the diode fabrication. Okay, so for this diode fabrication, for the LED or laser diode, the material used is called as luminescent material, which can produce light or photon. And typical materials such as gallium arsenide, indium phosphide, indium gallium arsenide. So these are the materials, that will be applied or will be used in LED fabrication because of the ability of this material to produce light when excited by a current. Okay, hopefully you understand this concept, yeah? Okay, so for this semiconductor material, for the diode fabrication, we are going to use what we call as extrinsic semiconductor, extrinsic semiconductor, in which we have two types of extrinsic semiconductor. The first one is what we call as a p-type. Okay, this is the same as what we have done in electronics, so I just repeat it again here. Okay, we have a p-type semiconductor and we have n-type semiconductor. So the difference is that for the p-type, it is doped with electron acceptor atoms, and for the n-type, it is doped with the electron donor atoms. Okay, so the band gap or energy gap, which is measured normally in electron volt, is the energy gap between the valence band and the conduction band in semiconductor. Okay, so I hope you have actually explained or informed before on this valence band and conduction band in semiconductor. Okay, so it can be said that this band gap or energy gap is basically we need to have a minimum energy that will be required in order to excite an electron from the valence band to conduction band. Okay, means that we need to have extra energy to move the electrons from the valence band to conduction band. So the movement of electrons from the valence band to conduction band and conduction band back to valence band. So this is the things that produce photon, in the LED or in laser diodes. Okay. In n-type semiconductor, the electrons are the majority carriers and the holes are the minority. Because from the word n-type here, okay, n-type is negative. So for negative type semiconductor, majority of the carriers are electrons and the minority carriers are the holes. Okay, so I put it here, the common dopant used in producing the n-type semiconductor are the arsenic and the phosphorus. Okay, so these are the common dopants used in n-type semiconductor fabrication. And it should be noted that the Fermi level for the n-type semiconductor lies closer to the conduction band than the valence band. So when the Fermi level closer to the conduction band, it means that it's easier for the electron to move from the valence band to conduction band, because the Fermi level is basically is the energy level, that is required, that is required by the electron to move up, yeah, electron to move up. So when we have the Fermi level which is closer to the conduction band, it means that the electron will be easier to move from the valence band to the conduction band. Okay. Whereas for the p-type semiconductor, the holes are the majority carriers. Okay. So this is the vice versa condition, and the electrons are the minority carriers. Yeah. Right. And the common dopants for the p-type semiconductor is or are the borons and the gallium. So these are the two materials used in p-type semiconductor fabrication. And for the p-type semiconductor, the Fermi level is said to be closer to the valence band than the conduction band. So that is why for the p-type semiconductor, electron, it is quite hard, or it is harder for the electrons to move to the conduction band, because the Fermi level for the p-type semiconductor is said to be located closer to the valence band. Okay, yeah? So by now, hopefully you understand what is meant by the bandgap energy, what is meant by the n-type semiconductor, and what is meant by the p-type semiconductor. So we know that n-type semiconductor will be having majority carriers are the electrons and the minority are the holes, and that should be the other cases for the p-type semiconductor, whereby the holes are the majorities and the electrons are the minorities. Yeah. So the bandgap energy is basically a difference energy between the conduction band and the valence band. Yeah. Okay. Hopefully you understand about this topic, this concept clearly. Yeah. Okay. So I put it here, figures which shows the bandgap energy in three different materials. We have the insulators here. Yeah, insulators. Insulators, we are having a very huge difference between the conduction band and the valence band, in which electrons will not be able to move from the valence band to the conduction band. Yeah, and this is the characteristic of insulators. We know that before. Whereas for the conductors, the conduction band and the valence band are said to be overlap with each other, in which we know from this condition, electron will be very much easier to move from the valence band to conduction band, and this is the case of conductors. Okay. Whereas for the semiconductors, there should be a very small difference of energy gap between the conduction band and the valence band, and somehow the electron, when it excites by a certain value of current, it can then move from the valence band to the conduction band. Okay, so these are the difference between the band gap or the energy diagram between the insulators, the conductors, and the semiconductors. So this is a concept that need to be understood before we discuss further on the LED and also on laser diode later on. Yeah. Okay. All right. So this is actually the things that we have learned before, just to put it in a graphical way. So what we have here on the left-hand side is your N-type semiconductor, and your right-hand side is your P-type semiconductor. And as what we have learned before, for the N-type semiconductor, we are going to have more, more electrons as the majority carriers, and the carriers are said to be located on the conduction band. Yeah, because the Fermi level for the N-type semiconductor is located quite near to the conduction band. Yeah, so it is easier for the electron to move up to the conduction band. So that's why we have majority of the carriers will be located at the conduction band. And as opposed to the P-type semiconductor, okay, we have majority of the carriers are the holes, okay, and the Fermi level is said to be located near to the valence band, and as such we can say that the electrons will be quite difficult for the electrons to move up from the valence band to the conduction band. So we can see that in the conduction band we have a very few electrons in the conduction band as compared to the N-type semiconductor. Yeah, so this is a graphical way to explain about the concept of bandgap energy and between the N-type semiconductor and the P-type semiconductor. Yeah. Okay. So the band gap, which is between the valence band and the conduction band, is the place where the excitation and recombination processes occur. Okay, so what is meant by excitation and recombination? So Basically, these are the processes that take place in the light generation, or I can say a photon generation in the LED or in laser diode. Okay, so excitation process is also known as a carrier generation. Yeah, carrier generation means that a generation of electrons and holes. Yeah. Okay, so in this process of excitation, the electron at the valence band, okay, will be provided by energy from the external source, in which this energy will be used by electrons to move, yeah, to move from the valence band to the conduction band. Okay, so this is what we call excitation process, the process of carrier generation, in which in this excitation process, the electrons which is initially at the valence band, which upon excitation by external source, which is the driving current, this electron will be having enough energy and it will leap over, or it will move to the conduction band. Yeah. So movement of these electrons from the valence band to conduction band will move its holes at the valence band. Okay, so now we have electrons at the conduction band and holes at the valence band. So this is what we call as a carrier generation. Okay, and then we have another process which is called as recombination process. So from the electrons which are now said to be located at the conduction band, yeah, due to this excitation process, yeah. So electron which is then located at the conduction band will eventually losses energy, and then it will then reoccupies the energy state of electron hole in the valence band. Means that electron which is located at conduction band will then I can say it will produce a photon, yeah, produce a photon, and due to this production of photon, this electron will then move down or go down to the valence band, and it will reoccupies the initial state of electron holes in the valence band. So the energy that is produced from this recombination process will emerge as a photon of light. So as I put it here in this diagram, so electron which is said to be in conduction band, okay, so we know that from the excitation process just now, yeah, from the excitation process, electron will move to conduction band. So in this recombination process, the electron will then go down, it will go down to the valence band, and the movement from the conduction band to the valence band will then produce the energy, yeah, produce the energy, and this energy will emerge as a photon of light, which is having its own lambda value or the wavelength value. Okay, so this is what we call as a recombination process, yeah, which is movement of the electron from the conduction band go back to its valence band. Okay, right. Any questions so far on this bandgap energy and also on the excitation and recombination process?
No, doctor.
No questions, yeah? Hopefully you understand it clearly. Okay, so let's proceed with the LED now. Okay, so by now, I hope you understand. In these diodes, yeah, in the diode, we have a process of excitation and recombination in which we're going to have the electron which will move from the valence band to the conduction band due to the excitation by current, and then the electrons will then go down from the conduction band to valence band, and this movement from the conduction band to valence band will produce light, yeah, will produce light due to this energy production. Okay, so in LED, the same concept that we have discussed so far will be applied, yeah, will be applied, and that is the equation, yeah, here's the equation that relates the bandgap energy. Yeah, bandgap energy is a difference, is the energy difference between the conduction band and the valence band. Okay, and as we have a diagram here, yeah, from these figures, we have the E1 is the energy at the valence band, E2 is the energy at the conduction band. So the band gap energy will be the difference between the E2 and the E1. So we labeled the band gap energy to be equals to Eg. Yeah. So the band gap energy values can be used to actually know. Yeah, we can use the band gap energy to actually know what should be the wavelength of light that will produce by this band gap energy. Yeah. So the equation used is Eg equals to hc over lambda, in which Eg is the band gap energy, h is the Planck constant, okay, c is the speed of light, and lambda is the emitted wavelength in the micrometer. Okay, the Planck constant is in the units of electron volt seconds, 4.13 times 10 negative 15, and it can also be written in terms of joule second unit by simply multiplying this value with the charge amount, which is 1.6 times 10 power of negative 19. Okay, so multiplication of the charge amount to these values in EV second will produce 6.62 times 10 of negative 34 joule second. Okay, so that should be the Planck constant value. Okay, and speed of light is 3 times 10 negative power of 8, and lambda is the wavelength in micrometer. So basically, from this equation, if we know what is the band gap energy for a semiconductor material, we shall then know what should be the lambda produced by this semiconductor material. Okay, I repeat again, yeah. Band gap energy basically is a specific value for a semiconductor material, yeah. So that's a specific value for semiconductor material. So for every semiconductor material, depending on the dopant used in this semiconductor material, we're going to have different band gap energy, yeah. So we can actually know what should be the lambda produced by this semiconductor material by simply knows what should be the band gap energy produced. So from this equation, if we know the Eg, we can then obtain the value of the lambda. Okay? All right. Okay, so the LED is basically a work or function based on a process known as a spontaneous emission. Okay, what is meant by spontaneous emission? So I put it here in this diagram. Okay, we have A and B. So A is what we call as the absorption. So I can say this is what we call as excitation process that we have discussed in the previous slide, in which initially we have the electrons at the valence band here at the E1 level, the energy level of E1 valence band. So this is the current, I can say the current which is said to be excited towards this material. So as such, the electron at the valence band will be having enough energy to leap over or to move to the conduction band. Yeah, to move to the conduction band. So this is what we call as the excitation process, or also known as the absorption process. Yeah. Okay. So this is the case when we have the electrons said to be located at this conduction band. Okay. So the electron at the conduction band will then go down to the valence band, and the movement from the conduction band to the valence band will emit light. Yeah, will emit light, and this emission of light due to this process of electron movement from the conduction band to the valence band is what we call as a spontaneous emission. Yeah, because of why? Because the electrons located at the conduction band is not stable. It's not stable. So the tendency for the electrons at the conduction band to move down to the valence band is very high. And due to this instability, the electrons will move down to the conduction band, and this emission of light, yeah, is what we call as a spontaneous emission. So in LED, the light is produced based on the spontaneous emission. That is why in LED, the light produced is incoherent. Yeah, it's incoherent because of this instability of electron position at the conduction band. Okay. Okay, so hopefully by now you have understand what is meant by spontaneous emission, which is a process used in LED for the light or photon production. Yeah. Okay, so now we're going to explain about the working function of the LED, how the LED works. Okay, yeah. So in LED, the PN junction, I mean the P semiconductor and N semiconductor need to be combined together, in which this will produce a PN junction. Okay, the same things apply in a PN diode that we have learned in electronics before. Okay, so when we when we connect the P material and N material, we're going to have a PN junction. And the PN junction basically will form a depletion region, yeah, depletion region. So what is depletion region? Okay, depletion region is a region whereby the electron from the N type, because we know that in N type we have majority carriers are the electron. So electron for the N type will move to the P type, yeah, will move to the P type, and going to have at the depletion region, the electron at the P type, I mean at this particular area, the majority of the charge will be electron. So that is why the potential that we have here is negative. Yeah, as opposed to this N type, because of the electron which has been moved to the P type material, the P type region. So we're going to have holes only at this particular region. That's why we have a positive charge at this depletion region. Okay, hopefully you understand why we have a positive and negative, because when we have a PN junction which is combined together, electrons at this region, or known as the depletion region, will move to the P-type semiconductor, and we're going to have a charge here will be negative because of the movement of electrons, and the charge here will be positive due to the holes which are said to be left behind by the electron which has been moved to the P-type material. Yeah. Okay, so that produces the depletion region. So at one time, the carriers will stop moving once we achieve the what we call as equilibrium state. Yeah, in which at the equilibrium state, there should be no more movement of electrons, because at this particular case, electron and holes are said to be locked in their covalent or atomic structures. Yeah. Okay, so in the stability or in the equilibrium state, we're going to have a potential, yeah, because we have a positive and negative charge density, and that's what we have learned in EMT before. Yeah, so we're going to have a potential difference between in this particular depletion region as V naught, yeah, because we have a positive charge and negative charge. Yeah, so V naught is said to be a potential difference between the N type and the P type at the depletion region. Yeah, at the depletion region boundary. Yeah. Okay, so this is a case without any voltage or current application to this particular PN junction. Yeah. Okay, so when we apply a current, yeah, apply a current in which fault biasing, we are going to have a case of the positive terminal will be connected to the P-type material, whereas the negative terminal will be connected to the N-type material or N-type semiconductors, okay, or we call that cathode and anode. Okay, I repeat again. For the fault biasing, the positive terminal of your power supply will be connected to the anode or the P-type, whereas the negative terminal of your power supply will be connected to the cathode of the N-type. Yeah? Okay, so let's say we assume that there should be a potential of V applied across the depletion region. Okay, so when we apply the potential V across the depletion region, the effect will be the potential at this depletion region will be reduced due in a value of V minus V naught, in which due to this reduction of potential at the junction, the width of the depletion region will be reduced. Okay, so in fault biasing, have to remember, or you have to know that when we apply fault biasing to the PN junction, the depletion region width will be reduced as a result of reduction of the potential in the depletion region. Okay, so when we have a very small depletion region, the results will be the electron in the N-type will be much easier to cross over the depletion region to the P-type semiconductor. Okay, now we know the consequences. Yeah, Means that when we have a smaller depletion region, the electrons in the n-type will be easier to move up to the p-type semiconductor, or to migrate to the p-type semiconductor, in which there should be a movement of electrons for the n-type to the p-type, and a movement of electrons for the n-type to the p-type will then resulted in a flow of current from the p to the n region. Okay, so this is the behavior, yeah, the behavior of the p-n junction that we have learned in electronics before. Okay, I repeat again. When you have a fault biasing, the results will be a reduction in the depletion region. So due to the very small depletion region, electrons from the n-type can cross over to the p-type, and due to this movement of electron, the current will be produced from the p to the n, and this will produce a current in the LED structure. Okay. Okay. So this is the case in the energy diagram graphical explanation. Okay. So we have the p-type here. Yeah, this is a p-type. This is the n-type. So this is your conduction band. This is your valence band, right? So we know that in conduction band for the n-type, we have majority of electrons in the n-type material. So due to the reduction of these depletion region, so most of the electrons can cross over to the conduction band of the p-type region or p-type material. And once we have a majority of the carriers in the conduction band of the p-type material, we're going to have a case of a higher probability of spontaneous emission produced in the p-type material due to numbers of electrons in the conduction band as a result of movement from the n-type material just now. Okay, so again I repeat, the electrons from the electrons from the n-type semiconductor can easily move to this p-type semiconductor due to the reduction of depletion region, reduction of depletion region thickness. So we have majority of the carriers here at your conduction band of the p-type will be electrons, and as a result, the electrons here at the conduction band will then move down to the valence band, and the movement of electron from the conduction band to the valence band will then produce a photon, a photon in the units of HF. I mean, photon produced is equals to HF, or the band gap energy, bandgap energy. So the movement from electrons from the conduction band to the valence band will produce the energy which is equivalent to the bandgap energy, because we have learned before that the difference between the conduction band and the valence band is the band gap. And the band gap is equals to Hc over lambda, or simply equals to Hf. Okay then. So this is what we call as fault biasing. So I mentioned it here that in fault biasing, the carriers will be moved across the junction. And this will then, we're going to have electrons here at the conduction band. And again, the movement of electrons from the conduction band to the valence band will produce a photon with the energy of band gap, which is equal to HF. Okay, so this is how the LED works. This is how the LED works. The difference between the LED and the diode that we have learned in electronics is that this photon produced, which is equal to HF, will produce light. As opposed to diode in electronics, the energy produced will not emit light, but it will just produce heat. Okay, so that's the difference. So how the LED can produce light? Because as I mentioned before, we have been using a luminescent material, in which luminescent material is a material which can produce light once we excite it with a current. So that should be the difference between the diode in electronics and the LED that we are learning now in this chapter. Okay, so this is another graphical diagram. Okay, we have a p-type material, and this is the n-type material. So basically it's the same as before. The difference is that in the previous, this is based on the energy diagram. Okay, so we can see that when we apply a voltage across the PN junction, okay, electrons at this n-type material will move forward or will cross over to the P junction. Yeah, will move forward to the P junction. Okay, and at this particular position or at this particular P-type material, there should be a process of recombination in which electron that has been transferred from the n-type to the P-type will be recombined with the holes, and as a result of this recombination, the photon will be produced with the value of energy bandgap of HF. Okay, right. So this is how the energy produced by the recombination process in LED. Yeah. Okay, basically there should be two types of recombination process. The first one is what we call as a radiative recombination. Yeah. So radiative recombination of carriers is a phenomena or a condition or a case whereby the energy is released with a creation of photon with a frequency or wavelength. Okay, it means that when the electron that is said to move from the n-type material to the p-type material, the electron will be recombined with the holes, and this recombination will produce the energy, and this energy is actually produced or released in a with the creation of photon. Yeah, with the creation of photon, and that's what we call this recombination as radiative, because this recombination produce or radiate light. Okay, we also have another type of recombination which is a non-radiative. Okay, a non-radiative is a case whereby when the electron and holes are said to be recombined, it will not produce photon, but it will produce heat. Okay, yeah. So also there should be a case of radiative recombination and non-radiative recombination of carriers in your LED, because somehow there should be we can say what we call that, these atoms, the I can say what we call that, and atoms which is not actually to make it in simple words. Yeah. Okay. So we know that in the process of doping, yeah, process of doping, we are doping the material with some material. Okay. Somehow we're going to have atoms which is said to be inactive. Yeah, I can say inactive atoms in which it will lead to unused atoms which cannot produce light. How to make it simpler? Yeah, the words that shall be used here. So I can say that non-radiative recombination is a result of recombination of holes and electrons of these particular atoms which are said to be how to make it a clearer way, yeah, in a simpler way. Okay, for radiative case is a recombination of electron and holes for these active atoms. For example, the gallium arsenide, all of these material, all of this material, yeah, that can produce light. Okay, so the radiative recombination is the recombination of this electron and holes of these particular atoms. But somehow we're going to have another atoms, yeah, another atoms, maybe other type of atoms, which is not of gallium and arsenide, yeah, and this particular recombination for this particular electron and holes will not produce light. Okay, and this recombination is what we call as non-radiative recombinations. Yeah. Okay, hopefully you understand this now. Hopefully, yeah. Right. So just to make it clearer for you, that recombination of carriers in LED light production can be divided into two types. The first one is radiative recombination, and the second one is non-radiative recombination, in which radiative recombination will produce light or photon, whereas for non-radiative recombination, it will only produce heat. Yeah, right. Okay, so I put it here that spontaneous emission of light from diode structure is also known as electroluminescence. Okay, so this is what we have mentioned before, luminescence, which is a light, yeah, that can be produced by this LED as a result of spontaneous emission. Okay, so most of the time you're going to have the light will be produced, most of the light will be produced at the p-type semiconductor. Yeah, at the p-type semiconductor, because most of the recombination process will occur at the p-type. Because why? Because electrons will move from the n-type to the p-type, and at the p-type material, the electron and holes will be recombined, and the light will be produced. Majority of the light will be produced at this p-type material. Okay, all right. Okay, this is about reverse biasing. So I'm not going to go into detail of reverse biasing because this is not a case of LED work function or principle. Okay, reverse biasing basically will be learned later in chapter 5 when we learn about the photodiode or photodetector. Yeah, photodetector basically work based on reverse biasing of PN junction. Yeah, so light source, laser diode or LED works based on forward biasing, whereas for photodetector or photodiode, it is based on reverse biasing of PN junction. Okay, but just to make it clearer for you, for the reverse biasing, as opposed to the forward biasing, the depletion region will be made widened. Yeah, will be widened. So when we have widened, depletion region, the potential difference will be higher. So as a result, the electron will be difficult to cross over to the p-type. Yeah. Okay. When the LED is said to be reverse biased, at certain level, the LED will be demolished. Yeah. Yeah. When you have the LED, when the LED is said to be reverse biased, initially it must be reverse biased for the LED to work. But when the LED is said to be reverse biased, the results will be we're going to demolish the LED when we apply a reverse bias to this LED. Yeah. Okay then. So for the LED, I did put here that the large emitting areas for the LED, which is not good as a laser diode. Yeah, so laser diode, the emitting areas will be smaller. Okay, due to I can say smaller spectral width for the laser diode as compared to LED. Okay, and also the light transmitted or light produced is incoherent. Okay, but the LED is said to be widely used for short distance transmission. Yeah, only for short distance transmission due to these reasons. Number one is that LED is cheap. Yeah, it's cheap. So one LED is cost about 20 or 30 cents only for one LED. It's very cheap. So one more thing is that the LED is quite linear in terms of light output versus input current. So we can say that after this, we're going to have a graph on the LED in which the LED, the graph of light output of the LED and the input current is linear. Okay. Number 3 is that the LED is stable in terms of light output with respect to the ambient operating temperature. Yeah, so stable in terms of light output. So basically there should be two possible structures of LED, which are the homostructure and heterostructure. I'm not going to go into detail of these LED structures, homostructure or heterostructures. So if you're interested, you can go through any textbook to learn about the homostructures and heterostructures of LED. The drawback of, most of the cases is that heterostructure is much preferred as opposed to the homostructure, because for the heterostructure LED, the light produced is said to be well directed. And one more thing is that in terms of recombination process, the light or this process is said to have a good confinement, because there is a special region for the recombination process. Yeah, there is a special region for the recombination process, and due to this, the light Yeah, the light is said to be well directed as a result of a very restricted active region. Yeah. Okay. So so most of the cases, heterostructure is preferred. Yeah, as compared to the homo structures. Yeah. Okay. So again, this is about the LED material which has been uh, mentioned before. So I put it here that there are many luminescent material that can be used to construct the LED. Okay, I put it here. For example, the aluminum gallium arsenide, which is actually used for short wavelength, and for long wavelength device, we have this indium gallium arsenide phosphide. So these are the metals that can be used to produce LED because of this luminescent material. Mean it can produce light. Yeah, it can produce light. Okay, so these materials are said to have different energy gap. Okay, I mentioned before, and due to different energy gap, the wavelength produced or wavelength emitted will also be different, which is based on this equation that we have discussed before, Eg equals to Hc over lambda, and we can simply write these equations to be equal to this, lambda equals to 1.24 divided by Eg, in which if we base on this equation, Eg is in eV or electron volt unit, while the lambda produced must be in micrometer unit. Okay, so by using this equation, if you know the Eg or the energy band gap, we can know what should be the value of wavelength emitted by this material. Yeah. So I put it here, the material that can be used, yeah, that is actually used. So for silicon and germanium, I can say is normally used in diode, yeah, in electronic diode. But for this LED material, we always use this kind of metal gallium arsenide, indium phosphide, and these are the materials that usually apply in LED fabrication. Yeah. So for example, if you have 1.24 electron volt energy gap for the gallium arsenide, the wavelength produced by this material will be 876 nanometer. So you can test this equation. I mean, you can test these parameters EV and wavelength by substituting this 1.424 in this equation, and as a result, you can have the lambda produced is 876. Yeah. So the same things apply for these other materials. So based on these materials, the EV, the energy gap, and the wavelength, we can say, or we can choose the proper material that shall be applied in our LED. Because if we base on this table, for example, if we want to work at 1550 nanometer wavelength, so we need to choose either indium gallium arsenide or indium gallium arsenide phosphide, because if we base on this table, these two material can produce light at that particular wavelength by simply adjusting the energy gap value. So how to adjust the energy gap or band gap value? This is based on the doping of material. So we can adjust the energy band gap value or the energy gap value by simply change the doping concentration of this material. So when we change doping concentration, we're going to have a change on the band energy gap of these materials. Yeah. Okay. All right. So this is basically the configuration of the LED. Yeah. There should be 6 configurations of LED that we can have. We can have the planar LED. We can have dome LED. We can also have surface emitting. We have edge emitting. We can also have superluminescence, and we can also have resonant cavity. So I'm not going to go into detail all of these 6 configurations. Yeah, you can read these on your own from the textbooks or from any sources. Yeah, but most of the time in optical fiber communication, the interest will only be on these 2 type, which are the surface emitting and the edge emitting LED. Yeah. Okay, so this is the typical spectrum for the LED. So we can say from this diagram that the spectrum of LED is very wide. Yeah, is very wide. So it can be said that the spectral width of LED is quite big. Yeah, the spectral width of the LED is quite big. That is why for the LED, it is not suitable to be used in a long distance application, because due to this very wide spectral width, the dispersion yeah, the pulse dispersion will be very big. Yeah, we're going to have a severe pulse dispersion, and this is not good for long distance communication. So it's only applicable for a short distance, less than 100 meters or less than 200 meters. Yeah, we can use the LED. Yeah, because of this very huge spectral width. Sorry, very huge spectral width. We're going to have a severe uh, pulse dispersion. Yeah, in your system. So that should be the effect of LED. So we seldom use the LED for long distance. I mean, we never use LED for long distance communication. For long distance communication, we always use the laser diode. Yeah. Okay. This is about this LED type. We have learned before. I mean, we have mentioned before. The surface emitting and the edge emitting. So I put it here. The diagram which explain the example of the surface emitting LED. So we can have the P type. Yeah, this is your P gallium arsenide. P type gallium arsenide. This is your N type gallium arsenide. So this is the P junction. Yeah, PN junction. Sorry, a PN junction with the dimension of the the N semiconductor width. Yeah, this is substrate thickness. This is the N type thickness. Okay, and we apply a fault bias. Yeah, fault bias. Positive terminal is connected to the anode. Yeah, anode, whereas the negative terminal is connected to the cathode. Okay, so the light is said to be emitted on the surface. Yeah, at the P junction. Yeah, at the P junction, as I mentioned before, most of the light will be transmitted at the P junction. Sorry, a P material, P type material. So at the P type material, the light will be emitted. Yeah, light will be emitted, and some of it will be emitted to the substrate. Yeah, and for the surface emitting LED, it is also known as a Burus LED. Okay, maybe the name of the guy or the scientist who developed this type of LED, Mr. Burus, I think. Okay, so the surface emitting has is high radiance characteristics as composed to these other type of LED. Okay, right. So I put it here that this is homostructure devices with edge well in a gas master. So this is the example of the surface emitting LED, which is the homostructure devices with an edge well in the gallium arsenide. So this is the edge, yeah, edge of this gallium arsenide substrate. Okay. So another one is edge emitting LED. Okay, edge emitting LED. So this is a very simple structure. We have the P region or P semiconductor. We have N region semiconductor, PN junction here. So the P junction or P type is connected to the anode, positive terminal, and the N region is connected to the cathode. So this is fault bias. So the light is said to be emitted at one side of this PN junction. Yeah, one side of the PN junction. So again, it also has high radiance characteristics. So light is produced in a very thin active layer. Yeah, so light emitted normally at the P junction, P region. Yeah, P region. So for the edge emitting LED, light is emitted at one phase, while the other phase is a reflector. So there should be no light emitted at this side. Yeah, it only be emitted at one side. Yeah, at only a single side. Yeah. Okay, so this is an example of edge emitting LED. Yeah. All right, so now we are going to learn about the characteristics of the LED. Right, so there are a few characteristics that need to be understood. The first one is efficiency, and then we have the output power. Then we have the output spectrum, followed by the bandwidth modulation, and also on the reliability. Yeah. Okay, so number one is efficiency of the LED. So as what we have learned, the LED principle is based on spontaneous emission. Yeah, there should be no amplification. So we can notify here that efficiency of the LED can be measured or can be obtained by these parameters, which is called as internal quantum efficiency of the LED. Yeah, eta. Yeah, eta of internal quantum efficiency. So this is based on the equation of R divided by RR plus RNR. in which RR is what we call as radiative recombination rate, okay, whereas the RNR is called as non-radiative recombination rate. Okay, so this is what we have learned before. I did mention here. We know that when there should be two types of recombination, correct? The first one is radiative recombination, which produce light, and we also have another recombination is what we call as non-radiative recombination. Okay, so I put it here basically that non-radiative recombination is a case whereby the energy is released in a form of heat. Okay, I did mention before. Okay, which is take place due to, okay, it's impurities. So the word is this impurities atom. Okay, that's the case, yeah. Because for radiative recombination, I did mention before, right? So we have this luminous material which has its atom. So when the electron and holes are said to be recombined, the photon will produce due to this radiative recombination. But there is a case whereby we have impurities, yeah, atomic and impurities, in which when these electron and holes are said to be recombined, no light will produce, but only heat. Okay, so this impurities atom. So that should be the word, yeah, impurity. Sorry for that. Impurities is the impurities atom is a case is atoms in which when the electron and holes of these atoms are said to be recombined, it will not produce light or photon, but it will only produce the heat. Yeah. Okay. So that is why for the quantum efficiency, the eta is equals to radiative recombination rate divided by radiative recombination plus the non-radiative recombination. Okay, so that should be the equation used to determine the internal quantum efficiency of the LED. In other words, this is the measured parameters, the parameters that can be used to explain about the efficiency of light produced by the LED. Yeah, efficiency of light produced by the LED. So I put it here that for a simple homojunction LED, the highest efficiency that it can be obtained is a 50%. Yeah, all right. So there should be another equation that can be used to determine the quantum efficiency values, which is based on tau divided by tau r, in which tau here is total recombination time, which include recombination time for radiative and non-radiative. Okay, tau r is radiative recombination time, whereas tau and r is non-radiative recombination time, in which tau, which is a total recombination time, can be calculated based on this equation. 1 over tau equals to 1 over tau r plus 1 over tau and r. Okay, so from this equation, we can obtain the total recombination time based on the values of radiative recombination time and also non-radiative recombination time. Yeah. So to calculate the internal quantum efficiency, we can use either these equations at the top here or these equations at the bottom here. Okay. So this is a parameter used to determine the efficiency of light, the efficiency of the LED to produce the light. Yeah. Okay. We have understand about the efficiency of LED. Number two is about the output power. Okay. So we have learned that the power emitted by the LED is proportional or is depending on the forward bias current. Okay. And due to the spontaneous emission by the LED, we can see that the output of the LED is incoherent. Okay, I mentioned before. And the characteristics of light coverage, yeah, the characteristic of light coverage of the, or I can say the emission of light coverage is somehow can be represented by what we call as lambation source. Yeah, lambation source. Okay, so this is a lambation source. Means this is the way how the light emitted. Yeah, how the light emitted by this planar LED source. Yeah, this is planar LED. So the characteristics of light emitted by this LED can be represented by a Lambrechian source, yeah, in which this is based on the equation of I theta. So I theta is a profile of light emitted and equals to I naught cos theta, in which I naught is the maximum amplitude of a light, yeah, I naught cos theta. Okay, so this is a Lambrechian intensity distribution of the planar LED, yeah. Okay, so the external power efficiency is defined to be a ratio of optical power emitted externally, which is the PE, power emitted, to the electrical power provided to the device, P equals to IV. Okay, so basically the external power efficiency, so there are two things here just now. Before this, we call this as internal efficiency. So internal efficiency is the ability of LED to produce light, okay? While for the external power efficiency is a ratio of the optical power which is emitted, okay, by the LED to the electric power which is used to operate the LED. Or you can say that P equals to IV, yeah. So I is the forward current, yeah, forward bias current, and V is the potential difference applied to the LED. Okay, so that should be the P, yeah, the electric power provided to the device, whereas the PE is the power which is emitted by the laser, by the LED, yeah. PE is the power or optical power which is said to be emitted by this LED. Yeah, so the external power efficiency is measured or is calculated based on the power emitted or the optical power emitted, the PE, divided by the electrical power multiplied with 100%. So if you base on this diagram, the PE is this red light here. That should be the optical power, PE, and the electrical power is just a multiplication of the I and also the V. Okay, so this will actually determine what should be the efficiency of the emitted power over the electrical power that operates the device. Yeah. Okay, so it can be said that the total recombination rate, which is the RR plus RNR, can be written to be equals to I divided by Q. Yeah? I is the forward current that is used in the circuit. So if you can recall back to this slide, yeah, back to this slide. So this is the I, which is the forward current. So I over Q, Q is the charge. So I over Q basically will be equals to the total recombination rate, yeah, recombination rate of the radiative and recombination rate of the non-radiative, yeah. So total recombination rate is equals to the total is the current injected divided by the charge amount. Okay, so we know that RR is the total number of photons generated per second, and each photon has energy of HF. Okay, yeah? So RR is total number of photons generated per second, and each photon has energy of HF. So due to that, we can write that from the, from what we have learned before, from this equation, yeah, which relates the internal quantum efficiency with the recombination rate of both radiative and non-radiative, we can then calculate the optical power which is said to be generated inside the LED by this equation. Yeah, which is the power or the internal power generated, the P int. Yeah, this is the optical power generated internally in the LED shall be equals to the efficiency of the internal quantum, or I can say the internal quantum efficiency multiplied with the current, forward current, divided by the charge amount, multiply with the Planck constant, and multiply with the frequencies, or it can be also be written as this equation because F is equals to C divided by lambda. So that should be the equation that can be used to calculate the optical power which is said to be generated internally within the LED. Okay, yeah? Right. And from this internal optical power, we can then calculate what should be the optical power PE emitted by the LED. So these two different things here, yeah. P in here is the internal power generated by the LED, whereas the PE here is the emitted power by the LED. So it can be seen that emitted power is portion, yeah, it's a portion of power from the internal power. Okay, so the power emitted or the PE can be calculated can be calculated based on the P in or the internal power by using this equation. Yeah, whereas the emitted power is equals to internal power generated multiply with the F constant multiply with the N squared divided by 4nx squared. So what is meant by these parameters? Okay, so you know that P in is internal power generated by the LED. And here is the refractive index, the medium of refractive index, which is the medium that we want to emit the power to. Let's say the LED is connected to the air, right? Connected to the air. So the N here is the refractive index of the air. Okay, N is refractive index of the air. Okay, and the LED is said to be fabricated from a material which is said to have a refractive index of Nx. So Nx basically is the refractive index of the material. For example, if the LED is made of gallium arsenide, so Nx here is the refractive index of the gallium arsenide. Okay, whereas this F is what we call as a transmission factor of the semiconductor to the external interface. Okay, so F is a transmission factor of the semiconductor to the external interface, and the F basically will be depending on the N, the index of N, and also the index of Nx. So that should be the dependency of the F, yeah, the transmission factor. Okay, so this is the equation that can be used to calculate the emitted power from the LED once we know the internal power. And once we know the transmission factor, because the N and the Nx can be obtained, yeah, because we know what are the surrounding medium and what should be the material that produce the LED, yeah. Okay, yeah. So this is the characteristics of output power. I mentioned before that the light output, the output power and the current are said to be linear, the relationship, yeah. So that's why we have for the ideal LED, the light output and the current are said to be linear, and this is the actual case, which is also normally linear. Or for example, here for this A is the gallium arsenide surface emitter LED, whereas this is for the aluminum gallium arsenide H emitter. So we can see that for the LED, relationship between the output power and the current are said to be linear most of the time. Yeah. Okay, then we also have the number 3 is the output spectrum characteristics. Okay, so this is what we call as a typical spectrum produced by the light source. Okay, so from this spectrum we can extract an important information which is called as full width at half power, or also known as full width at half maximum. It's the same, yeah. Full width half power or full width half maximum is the same, which is basically is the width of spectrum curve measured between points on the y-axis which are half the maximum amplitude. Okay, which means that if the peak is said to be at 100%, so half power is at 50%, right? So there should be a width of spectrum, at 50% half power. Yeah, and the width of the spectrum, which is a span between lambda 1 and lambda 2, yeah, lambda 1 and lambda 2, is what we call as a full width at half maximum, or also known as a spectral width, yeah, also known as a spectral width. So it can be said that full width at half power or spectral width are the same parameters, yeah, the same parameters. Okay, so LED, we know that for the LED, due to the spontaneous emission process, the spectral width of the LED will be it's wide, yeah, it's wide as compared to laser diode, yeah. So we normally use the data lambda. So this is a symbol for the spectral width, yeah. Okay, and then we have a spectrum which is depending on the doping level. Yeah, so if we can base on these a case that if we have heavily doped material, they're going to have an increase in the spectral width as opposed to the material which is said to be lightly doped. So basically, a doping level will also give effect on the spectral width values. Yeah. Okay. So I put here that high doping level, we're going to have a smaller bandgap energy. Okay, that should be the case. And then we have a different output spectrum for the case of surface LED and edge emitting LED, as LED stands for surface emitting and edge LED stands for edge emitting. So it can be said that surface LED or surface emitting LED is said to always have wider spectral width as opposed to edge emitting LED, yeah, because of the doping level of this material. Okay, and sorry, for the third one will be on the temperature effect on the output spectrum. It can be said that when we have different temperatures or different operative temperatures for the LED, the results will be changes on the output spectra, in which we can see that there should be a higher spectral width when we operate the LED at higher temperature. Yeah, because if you base on this diagram, 0 degrees, 30 degrees, and 60 degrees. So for 60 degrees, it can be noted that the spectral width for the LED is higher, yeah, or is bigger as compared to smaller temperature. This is due to greater energy spread in current distribution, yeah, for the higher temperature case, yeah. Okay, then the next characteristic is the modulation bandwidth. Okay, so I put here the difference between the electrical 3 dB bandwidth and the optical 3 dB point or 3 dB bandwidth. Okay, so hopefully by this diagram, you can differentiate what is meant by the electrical bandwidth and the optical bandwidth. Yeah. Okay, so the optical bandwidth I put here is the electrical signal power which is said to drop to half its constant value. Okay, so it means that initially we have 1. So when it dropped to 0.5, drop to half of its value, so the width of these frequencies is called a optical bandwidth. Whereas for the electrical bandwidth, the case whereby the electrical power is reduced by 3 dB. So 3 dB means that the power reduced to 0.707 out of 1 normalized current, yeah? So that should be the electrical 3 dB point, and that should be the electrical bandwidth. So hopefully by now you can differentiate between the electrical bandwidth and the optical bandwidth. And this is the equation that relates the optical bandwidth and the electrical bandwidth. B equals to F divided by set of 2. B is the electrical bandwidth and F is the optical bandwidth. Yeah. Okay, I'm not going to go into detail of these mechanisms for modulation bandwidth. So basically, these are the mechanisms that can be used to determine the bandwidth. Yeah. The first one will be doping level. Yeah. So doping level is critical in determining the modulation bandwidth. Number 2 is reduction in radiative lifetime. And number 3 is parasitic capacitance of the device. So I'm not going to go into detail of these. So if you're interested, you can go through these mechanisms in any textbook, yeah, to determine on how this will affect the modulation bandwidth. Yeah. Okay. So number 5, the fifth characteristic will be on reliability. Okay. So there should be a case whereby the LED can be easily degraded, which is the early or infant failures, and this is very random. Yeah, random, and normally this is due to manufacturing defects. Okay, we also have the gradual degradation. That means that as time goes by, as we increase from as we use these LED from time to time, there should be a gradual degradation where it can be divided to 2 types, where we have the dark line defects and also dark spot defects. Yeah. Okay, for the dark line defects, we have a growth of dislocation. in active region. So we know that active region is the place whereby the recombination process occurred. So when we have a growth of this location, yeah, a growth of this location, by right, there should be a reduction in recombination process, and as such, there should be a reduction of light produced, yeah, and for the dark spot defects, a growth on precipitate type defect, which is the impurities, yeah, in active region. So as the impurities increase, again, the efficiency will be reduced, yeah, and when we have reduced efficiency, so it can be said that the LED has been defected, yeah, defected. Okay, okay, so this is the homogeneous degradation of a LED. Number one, it can be due to migration of impurities into active region. Okay, so basically, when we have increasing impurities in the active region, so impurities will actually produce a non-radiative recombination, right? As we have discussed before. So when we have increasing non-radiative recombination process, as such, the internal quantum efficiency will be reduced. Yeah. So we can go back to this equation before. This equation, yeah. So when we have increasing non-radiative recombination rate as a result of increased impurities, so this internal quantum efficiency will be reduced significantly. Yeah. So all of these will reduce the LED efficiency, and it said that the LED has been degraded. Yeah. Okay, the same things applied. This the second case will be defect in recombination process. Okay. Somehow there should be vacancies in which there should be a case whereby the holes is said to be unoccupied, yeah, unoccupied by the electrons. Supposedly, when the electron move from N type to the P type semiconductor, it should fill the holes, yeah, it should fill the holes, and when we fill the holes, recombination process occurred, yeah, and we have a relative recombination, and light will be produced. So somehow, when we have a problems when the light, I mean, the electron will move, but not all the holes will be filled by this electron, and as such, there should be a vacancies in the P-type semiconductors, and as such, the LED is said to be degraded. So all of these are a material degradation effect. Yeah. All right. So before we end this lecture number 7, we need to understand well on the coupling of light from the LED. Yeah. So this issue is very important, especially in the optical communication system. Yeah, because when we want to transfer the light from the LED to these fiber optics, the coupling of light is very critical issues. Yeah, it's very critical issues. Okay, so there should be more loss accounted when we want to couple the light from the LED to the fiber. Yeah, because we have the LED, we have the fiber, which is said to be put close together in order for the light from LED to be coupled to these fiber optics. Yeah, but not all light from the LED will be coupled to these fiber optics. So that's why I put it here that more loss will be accounted when we try to couple the light from the LED to these fiber optics. Yeah. Okay, so in order to measure this coupling efficiency of light from LED to the fiber optics, our approach is simplified. Yeah, we go for simplified approach. In that, by assuming for step index fibers, all incident light on the exposed end of the fiber core within the acceptance angle theta A is coupled. Okay, so I put it in a very simple approach in which we have the fiber optics, right? We have the fiber optics. We have learned in chapter 2 that every fiber optics or every fiber is characterized by its own acceptance angle, yeah, theta A. So it means that if the angle of incidence from outside or from the air is smaller than theta A, so light will be coupled inside the fiber optics. But if the angle of incidence is higher than theta A, yeah, bigger than the acceptance angle, so light will not be coupled into the fiber optics. Yeah. So I put here that all incident light from the LED, yeah, all incident light from the LED within the acceptance angle theta A is said to be coupled, yeah, into the fiber optics. So I put here that all incident light greater than theta A will not be coupled into the fiber. So this is known, yeah. So equation from chapter 2. So we have learned that from chapter 2, numerical aperture is equals to n naught sine theta A. N naught is the medium of air. If we consider that the coupling is applied in the air environment, yeah. Okay. So for that, n naught is 1. Okay, and theta A is the acceptance angle, so we can write theta A as equals to arc sine of numerical aperture. Yeah, so this is the equation that relates the acceptance angle and the numerical aperture. Okay, so now we can calculate the coupling efficiency for the light coupled to the fiber optics by using this equation. Okay, so we can use a lambation intensity distribution. So we have learned before, if you can recall, if you can refer back to the previous slide, yeah, on the output power. Okay, we know that the light distribution from the LED point is said to be following this lambation intensity distribution. Okay, we have I naught cos theta. Yeah, so this is the profile of light produced by the LED. So we can use that profile to calculate the optical power, to calculate the coupling power, okay, based on this equation. So coupling efficiency is equals to PC. So PC stands for the coupling power into the fiber, okay, and PE is the emitted light from the LED. So we have seen this PE before, right? Emitted light from, so emitted power from this LED. So the coupling efficiency is coupling power into fiber divided by emitted power from LED. So we can use this equation, see that the coupling power is the integration from 0 to theta A, yeah, only from 0 to acceptance angle, whereas for emitted power, the integration is from 0 to pi over 2. So when we proceed with the integration, end up, we are going to have the value of coupling efficiency here as equals to sine squared of theta A. Yeah, sine squared of theta A. And from what we have learned before, numerical aperture is sine theta A. So sine squared theta A is equals to numerical aperture squared. So coupling efficiency for light from the LED to the optical fiber can be calculated equals to NA squared. Yeah, NA squared. So that should be the coupling efficiency of the light from the LED to the optical fiber. Yeah. Okay. So in general, we can use this diagram to relate the power produced by the LED up to the fiber optics structure. Okay. So this is our LED here. So we know that LED is operated by forward bias current I, and the V is potential difference which is applied across the LED. So the electrical power that is connected to the LED is equals to IV. Okay, so this is understood. So inside the LED, as what we have done before, we have the internal quantum efficiency, the eta internal, yeah, which is, if we can recall back, is the ratio between the radiative recombination rate over the total recombination rate. So that gives us the eta, or the internal quantum efficiency. And based on this internal quantum efficiency, we can calculate what should be the amount of internal power generated by the LED itself. Yeah. So the internal power generated by the LED itself is equal to this equation. The internal quantum efficiency multiplied with the Planck constant, multiplied with the speed of light, multiplied with the I is this I, the forward current, but divided by the charge amount and the lambda, which is the wavelength of the light produced. Okay, and at the output of the LED, we are going to have the emitted power, the PE. So PE is the emitted power by the LED, which can be written in terms of the internal power generated. So PE is P int Fn squared over 4 nx squared. So we have seen this equation before, which is the emitted power by the LED. And further on, this emitted power shall be then coupled into the fiber optics, where it is equal to the PC. PC is the coupling power to the fiber optic, and it is equal to the coupling efficiency NC multiplied with the emitted power. So basically, coupling efficiency is equals to coupling power divided by emitted power. So these are the relationship between the power used to generate the LED up to the power coupled inside the fiber optics. Yeah, hopefully by this you can summarize, you can understand well on the power values that can be calculated in the case of LED. Yeah. Okay. Any questions so far on these topics of LED?
So far, okay, doctor.
Okay, yeah. Hopefully you understand it quite clearly, hopefully, yeah, on these topics of LED. Okay, so let us proceed with these examples on this LED before we end the class today. So for this example number one, we have a informations of radiative and non-radiative recombination lifetimes of the minority carriers in the active region of a double heterojunction LEDs. And the value for radiative recombination time is 60 nanosecond. For non-radiative recombination is 100 nanoseconds. Yeah. So given that the peak emission wavelength by this LED is 0.87 micrometer with a drive current of 40 milliampere. Okay, yeah? So this is the information given for the LEDs. Yeah? So number one, determine the total carrier recombination lifetime. Yeah, total carrier recombination lifetime. Number two, power internally generated within the LED. Okay, so number one is to calculate the total carrier recombination lifetime. And number two is to calculate what should be the internal power generated, which is the P int, yeah? P int. So basically for number one, the total carrier recombination lifetime can be based on this value of radiative and non-radiative. If you can recall back, we can use the equation of 1 over tau equals to 1 over tau r plus 1 over tau nr. Okay, so that is the equation used to calculate the total carrier recombination lifetime. And basically, from this information of total carrier recombination lifetime, we can use it to calculate the internal quantum efficiency. Yeah, we can use it to calculate the internal quantum efficiency, in which the equation is tau, or total recombination time, divided by radiative recombination time. Okay, so that's how you obtain the internal quantum efficiency. So we can use this information of internal quantum efficiency together with the lambda, together with the drive current, to calculate the power internally generated within the LED. Yeah? Okay, so how to answer this question? Let us proceed to the solution for this example. Yeah. Okay, so this is a solution for these questions just now. Right, so I give it here that radiative recombination time is 60 nanosecond, non-radiative is 100 nanoseconds. So from these two information, we can use it to calculate the total recombination. Yeah, 1 over tau r plus 1 over tau nr. So we have seen this equation before, right? In a efficiency characteristics of the LED. You can refer to the notes. Okay, so from this calculation, we can obtain the tau, the total recombination time, to be equals to 37.5 nanoseconds straight away. Yeah. Okay, so from this information of total recombination time, we can use it to calculate the internal quantum efficiency, the ability of the LED to produce light, which is the tau divided by tau r. So we're going to have 37.5 nano over 60 nanoseconds. So the answer will be 0.625, and in percentage, it is 62.5%. Okay, so that should be your internal, that should be the internal quantum efficiency. So from what we have learned before, the internally power generated, the P int, can be calculated based on this equation. Yeah, the internal quantum efficiency multiplied by H Planck constant multiplied by C multiplied by I divided by Q over lambda. So based on the questions, the I and lambda have been provided to you. Yeah, I is 0.87 micrometer, I is 40 milliampere. So based on that values given, you can calculate the internal power generated in the LED by substituting the information. Okay, this is the efficiency 0.625. Okay, H use is in EV, yeah, not in, sorry, in Joule. In Joule second, not in EV. Okay, in Joule. Yeah, C is speed of light, R is the current 40 milliampere, Q is the charge amount 1.6 times 10 negative 19, and the lambda is 0.87 micrometer. So the answer for the internal power generated is 35.67 milliwatt. So this is the internal power generated by the LED. Okay, so basically it will be depending on your internal quantum efficiency. If you have higher internal quantum efficiency, so the internal power generated will also be increased. Yeah. All right. Hopefully you understand these questions clearly. Okay. So let us proceed with the next example here. Okay. Number 2. It is given here that the external power efficiency of an indium gallium arsenide phosphide or indium phosphide planar LED is 0.75% when the internally generated optical power is 30 milliwatt. Okay, so if the potential difference across the device is 1.6 volt and refractive index of indium phosphide may be taken as 3.46, determine the transmission factor for indium phosphide air interface. Okay, so we are given here that the external power efficiency, yeah, this is the eta EP, if you can recall back, that the eta EP is equals to PE divided by the P. PE is the emitted power, P is the electrical power provided or supplied to the LED, yeah, in which P equals to IV lah, yeah. Okay, so based on this information, we are given the current, we're given the voltage across the LED, we are given the refractive index of this material, indium phosphide. So we need to determine what is the transmission factor for the indium phosphide, which is the F lah, yeah? If you can recall back, this is the F parameters. Okay, so how to calculate the F? Right. So we need to actually find the PE. Yeah, need to find the PE first, in which we know that PE, we had the equation for that. Yeah, you can remember, if you recall back, PE has the relationship with the internal power, the F, yeah, the F, the current. So all of these equations, you can refer back to the equations before. Okay, so let's have a look at the solution for this example on calculation of the F. Okay. Right. Okay, this is the case, yeah, for the second questions. So we are given that the NEP, yeah, the NEP, which is the efficiency, emitted external power efficiency, is equals to PE over P. This is the equation that we have seen before. So the NEP is given to be 0.75% or 0.0075. Okay. So it was given that the internal power provided is 30 milliwatt. Yeah, if you based on the questions, the internal power generated is 30 milliwatt. The current provided is 37 milliampere. The refractive index of the indium phosphide is 3.46, and the voltage is 1.6 volt. So basically, from these informations given, we can use it to calculate the P. P is very straightforward, I times V. Whereas the PE can also be calculated partly because we have the P in value here. Yeah. Okay, so this is the PE. It can be calculated based on this equation here. The P in is given. The N is known because N equals to 1, because the emission of LED is towards the air, so N equals to 1. while the Nx is the refractive index of the material, which is 3.46. Okay, so the unknown is F, yeah? So F is to be calculated. So from this equation, we have learned that from this equation, yeah, NEP, eta EP is 0.075. So we can write that the PE will be eta multiplied with the P, which is 0.0075 multiplied with the power, electrical power is IV, and this will be equals to 30 milliwatt multiplied with F, which is unknown, multiplied with 1, which is air, environment, and divided by 4 times the 3.46 squared. Okay, so we substitute I and V straight away. So I is 37 milliwatt, V is 1.6 volt. So end up we can find the F, which is the transmission factor, is 0.7087. So means that the transmission factor for the indium phosphide and air interface is 0.7087. Yeah. Okay. So let us proceed with the next example. Do you have a class after this, 11?
Yes, doctor.
Oh, you have a class. So we're going to have a look at the final example before we stop the class. We end the class today. Okay, so the last example for today is on this question. We have a gallium arsenide planar LED which emit a wavelength of 0.85 micrometer. It has the internal quantum efficiency of 60% and passing a forward current of 20 milliampere. We need to, number one, estimate the optical power emitted by the device into air and determine the external power efficiency if potential across the device, potential difference across the device is 1 volt. Okay, assume transmission factor at gallium arsenide A interface is 0.68 and refractive index of gallium arsenide is 3.6. Okay. Okay, this question is about the gallium arsenide LED. The wavelength of operation is 0.85 micrometer. Okay, so the internal quantum efficiency is 60%. Output current is 20 milliamp. The question is to estimate the optical power emitted, which is the PE lah, yeah. This is the PE, so we can find the PE. Yeah, we can find the PE by using the equation that we have seen before. Okay, so the PE can be calculated based on the. But before we can calculate the PE, we need to calculate first the P in. We need to have the P in first, because the P in should be there to be used in calculating the optical power emitted. And once we have the PE, we can find out the external power efficiency by simply have a ratio between the PE and the P. Okay, so basically two things to be obtained here. The PE and also the eta of EP, yeah? Okay, so let's have a look at the solution for this example. Right, yeah? Okay, so for this example, we have a information is given here. Lambda is 0.85. Eta internal is 60%. The R is 20 milliamp. V is 1 volt. The F is 0.68. And the eta of gallium arsenide is 3.6. Yeah? Okay, so we can calculate the P in straight away, which is the internal power generated. Based on this equation, the eta internal is 0.6, H is 6.62, C is 3 times 10 power 8, I is 20 milliampere, Q is 1.6 power 19, lambda is 0.85. So from here we can calculate the internal power generated is 17.52 milliwatt. Okay, so this is the internal power generated. So from this internal power generated, we can use it to calculate the emitted power, which is based on this equation. Okay, internal power is from the previous solution. F is given, N is 1, and X is 3.6. So by this calculation, your emitted power is 0.23 milliwatt. See, internal power is 17.52, but the emitted power is only 0.2, which is a very huge difference, right? Yeah, very huge difference. Yeah, P in is 17.5, which is the internal power generated, but the emitted power is only 0.23 milliwatt. Yeah. Okay, so from these obtained values of PE, we can simply write the external power efficiency, which is P over P times 100%. So PE is from the previous solution. P is the electrical power, which is IV, which is 20 milliwatt. So from the ratio, we can find that the NEP or the eta external power is 1.15%. So it's very small. Yeah, the efficiency is only 1.15%. So it's very small. Yeah. Okay, I think that's all for our class today. Okay, so I'm going to share the videos and also the slide, sorry, the solution after this. Okay, so thank you very much. Have a nice weekend ahead. Any questions before we end the class?
Can you please share the QR code, doctor?
Oh, okay, the QR code. I'm going to share it again. Okay, then. Okay, thank you very much. Yeah, so meet again next week. Yeah.
Thank you. Uh,
Okay,
have a
thank
nice
you.
Okay, thank you so much, doctor.
Thank you. Thank you very much.
Assalamualaikum.
Waalaikumsalam.